Good morning and good afternoon, depending on where you are. I want to thank you again for joining us for today's session, Effective Process to Characterize and Find External Interference. My name is Gloria Warland. I'm with Viavi, and before I introduce our speaker today, I have a few housekeeping tips. The session today is being recorded, and it will be available in a few days for sharing or revisiting based on what you want to hear again. All lines are muted, but questions are welcome and encouraged. If you have a question as we're going through the session today, please use the Q&A session at the option at the bottom of your screen. We will have time at the end of this session to address as many questions as possible. If we don't get to one of your questions live through the webinar, we will reach out to you after the webinar and get that information, have someone contact you to get your questions answered. We also have a short survey at the end of today's session, and we do appreciate your feedback. It informs us on topics that you may want us to cover in upcoming events. So now I'm going to introduce our speaker today, Eduardo Inzunza. He is a Viavi product line manager. He's been in the test and measurement arena for more than 25 years, has immense technical expertise. He's been with Viavi for over 11 years, and he has, as I mentioned, has deep technical knowledge as well as field experience. Dan Smeja was going to be joining us today. He unfortunately had a change in his schedule, but for those that know him, he does provide sales support and wireless technology expertise to our customers, and he welcomes your outreach, as does Steve Gale, whose email is also on the front screen there. I'm going to turn this over to Eduardo, who's going to lead the session. Without further ado, take it away, Eduardo.
Thank you, Gloria, and hello, everyone. So in this session, I'm going to be talking about uplink interference. Probably I'm going to elaborate a little bit more about interference in 5G, with the understanding that 5G comes, let me call it, in different flavors. But before I get into it, as Gloria said, please feel free to reach out. These are the emails. You probably might know Dan, Steve, or myself. If you have any questions now or later, or anything that you want us to cover in the future, as Gloria mentioned, please let us know. Okay, so I'm going to start with just briefly the interference analysis overview, because we have covered this topic in previous webinars, but I'm going to be spending a little bit more time on these two aspects: the 5G TD autogated spectrum, which it's important, is different from what we have seen or experienced before in interference on low frequencies or low bands. So that's important. I'm gonna try to do a demo here. I don't have a great reception on a 5G TD signal. However, I'm gonna give it a try to testing. Also, I'm going to be talking about interference post-analysis. One of the things that we have seen is that interferences are not always there, are not static in frequency or time. And for some of them, it's kind of difficult to find them and to get the profile or to characterize that interfere. So I'm going to be showing you kind of a technique here on how to analyze those intermittent interference signals. And after the characterization, we're going to be talking about how we can find the source of interference. So let's go into the three main categories that we have for interference, and this is, I will say, probably more applicable into 5G TDD, just because here in time division duplex, the synchronization and timing, it's key. It's really important. And if we have a problem with time, then we're going to have interference, and that's due to the fact that the radios are transmitting frames. They should be transmitting roughly at the same time. Certainly, there's a little bit of time to compensate for propagation delay. However, if there's radio that it's out of sync, that gap that it's allowed for propagation delay, it's going to be exceeded, therefore causing interference that the downlink is going to be overlapping with the uplink. So that's important. That's basically what we have talked before about time error and self-phase synchronization. So that's the second group. So we have the traditional two groups of interference. One is caused by passive intermodulation. The other one is caused by external interference. The third one is the cause by timing. So again, these are the three main categories that typically they reflect as an interference problem in the uplink. So we talk about self-phase sync. We've talked a couple of times about PIM detection and how impacts PIM and LTE into my 5G mid-band or C-band radios. Now I'm going to be talking a little bit more about external interference. So for external interference, typically, even though that interference exists and might be hitting the radio transmission or the downlink, typically it's more important to kind of analyze the uplink. The reason for that is that the uplink or the mobile is transmitting at significantly less power than the radio. So the mobile, it's more sensitive to any kind of interference because of that fact. And then the other fact is that typically the interference sources are in closer proximity to the mobiles than into the radio itself. So certainly the communication path that is mostly impacted is the uplink or the transmission of the mobile to the radio. Now, which are the sources of external interference? Multiple. And these might also kind of vary on typically where we see them in frequency. So, for example, cable leakage, that's typically in the low bands, billboards, smart grids as well. Welding machines, that actually varies. But the interesting thing about these kind of welding machines and industrial equipment is that it happens in a frequency hopping manner. So if you see how they behave and how they hit the uplink, is not in just a constant signal that is always in the same frequency, but it changes in frequency. It has a frequency hopping kind of behavior. Video cameras and broadband amplifiers, we've seen them in different bands, different problems, even cordless phones. Sometimes the companies, enterprises, they use a lot of cordless phones. And what happens is that sometimes the phone is looking for the base. And when it looks into it, it scans through multiple tones to see where the base might be. And sometimes those phones actually scan well beyond of the frequency that they're supposed to work and hits the uplink. So sources of interferences, external interference, this is many of them. Now, how can we find and do a proper interference analysis? Typically, we received the KPI, a key performance indicator from the management system, indicating that there's a problem on a certain area. But as a best practice, the first thing that we need to do is to know how that interference looks like. Because if we just receive the note or we understand there's an area that there interference, and we just go and find it, it's going to be extremely difficult because we don't know exactly what we're looking for. And there might be multiple interference signals. So first and foremost, it's really important first to understand how that interference behaves and where it is in frequency, And with that information that we call the interference profile, now that we know how it is, how it behaves, we can go and hunt it, or we do an interference location or interference finding. But yet again, it's really important to know how that interference is, how it behaves. And during the process of finding it, first, typically it's to find a location or area. That certainly this can be done automatically by doing a drive test with the interference advisor, or it can be done in a conventional way with triangulation using a broadband antenna. That's okay. It takes more time, certainly, but sometimes I've seen people still doing it. It's fine when you have an environment that doesn't have a lot of buildings and stuff, because certainly one of the things that you want to avoid is a lot of reflections. So if the interference is reflecting through buildings, then we're going to be doing a lot of multiple triangulations that sometimes they're going to be pointing in a different location where the interference is. So my recommendation is just to do a drive test with interference advisor. That's going to help you getting a lot of the data samples, and the system automatically it's going to be able to narrow down the location where the interference is. And once we know the location, then it's a matter of finding the device or the amplifier that it's creating that interference. And for that is just a matter of doing a walk test with a directional antenna. And that's going to point us exactly in where that device is. And then once we find that device, we can just mitigate or turn it off the device that is causing the problem. So these are the key steps. All of them are very important on how we're going to be able to find external interference. So let's talk a little bit more about 5G. So 5G, as I said, it exists in different ways, different options, I guess. In the standards, they call it, they have different numerology, meaning that the 5G might have different types of configurations. Let me give you a couple of examples. 5G, if it's deployed in the low bands, anything, let's say, below 2 gigahertz, that means that deployment, it's going to be as frequency division duplex, or FDD. So in essence, that's going to be very comparable to LTE. Now, if it's deployed in, let me call it the mid band, anything above 2, or certainly everything that it's above 3 gigahertz, all that is time division duplex or TDD based. And that's, again, kind of a very different than before than with FDD, because even if in FDD we have a clear distinction between uplink and downlink because they are in different frequencies. In the case of time division duplex or TDD, the downlink and the uplink are being transmitted at the same frequency but different timing. So that creates a little bit of a complexity in terms of, if we have an interference in 5G TDD in mid-band, how we're going to be able to characterize that interferer. And for that, certainly we have to have the ability just to analyze the uplink timing or the spectrum of the uplink. Now, that's one challenge. The other challenge that we're seeing is that there are different ways in which the frame is transmitted. I'm going to elaborate a little bit on the frame a little bit later, but let's go through an example here. This is a time division duplex signal. Actually, have a couple of channels on my left-hand side. Let me see if I can point it. So I have a couple of TDD signals. This happens to be LTE TDD. So 20 megahertz each one of them. And as I said, on TED, we have to have the ability to look into just the uplink timing. So we have a dual gate sweep spectrum technique, which we see the same signal that we're analyzing here. So I've centered here on 2.538, same center frequency, but here instead of having the analysis on a frequency domain, I have it on time domain. So the same signal that I have here on the left is exactly the same signal that I'm seeing right here on the right-hand side on the top half part of my display, but it's on time domain. And it's important because now I can make a distinction between the uplink and downlink. So as you can see, I have a lot of traffic. That traffic, it's my downlink. And every once in a while, I get traffic from my uplink. Main difference is that, as you can see, the traffic from the downlink is roughly the same power level. Why? Because it's coming from the same radio. Whereas on the uplink, the power might be different because it's coming from mobiles. But now here in LTE TDD, it's all bit of straightforward with a dual gated sweep spectrum, because again, we have this clear distinction between downlink and uplink. And the other reason is that here in LTE, the assignment between downlink and uplink is based on a subframe. So based in 1 millisecond or more. So we have a good time as well, just in all the frames here, LTE, 5G, one frame is 10 milliseconds. So as you can see, these gaps or these transitions between downlink and uplink, this uplink is actually happens to be a little bit over 1 millisecond. So that is very helpful because now we can see the uplink clearly, and we can assign two gates. Those gates are the gates in which the our spectrum or analysis is going to be triggered on. And why we have two gates? Because here with two gates, we basically improve the probability of intercept of an interferer. So if interference is intermittent, we're going to be able to see it if we have the analysis on both uplink slots. So as a result, here down, we see the spectrum. And as you can see, we're only looking for the uplink. And as it happens here, we have an interference that we can clearly see because of this dual gate capability. Now, this is for LTE. What happens with 5G in TV? So a couple of distinctions that I want to make between LTE and 5G. One is something that I briefly mentioned, is the fact that we have different options in 5G. It's called numerology. And with that numerology or with all these options, we can have different subcarrier spacing. Subcarrier spacing, what that is basically here, if we have a 5G signal, mid-band, the bandwidth can be anywhere between 5 and 400 megahertz. Typically, what we have seen in the C-band, it's anything between 20 and 100 megahertz wide. Now, this signal is composed of multiple subcarriers. The width of each subcarrier, it's defined by the numerology. So if it's a numerology 0, we have a 15 kilohertz of width of subcarrier. Okay. Now, this happens to be the same as with LTE. LTE was only one configuration. It was only 15 kilohertz. In the case of 5G, we have all these different options. So two key distinctions in 5G low band and 5G mid band. In 5G low band, it's always 15 kilohertz. In mid-band, there are different options, but typically what we have seen is that all of them are 30 kilohertz. And why that is important? Because of two main reasons. One is where we're going to be doing the analysis on the uplink. And the other one is that if we get a report saying that we have a problem in PRV 58. Where is that PRV and how wide is that PRV? PRV stands for the physical resource block. I'm going to elaborate on this a little bit later, but let's look into the first challenge, which is where the uplink is. So again, if I look now the same signal, but in time, I have one frame, I have my 10 subframes. So this is standard, this is the same as LTE. The difference though now is that if I have a subcarrier spacing of 15 kilohertz, one slot, it's basically the size of one subframe. Now, if I have a 30 kilohertz subcarrier spacing, as you can see here now, we have one slot as a half of a subframe. So we have now more slots. So as you can see, the timing for each one is being reduced. Now, the timing for each slot is about 35 microseconds. And I'm pointing this out because doing the analysis of 5G interference uplink, it's a bit more precise due to this reason in mid-band. So, for example, here we have the assignment of different frame types that can be done by each of these slots, which, by the way, each slot contains 14 symbols, okay? So that's basically how also a physical resource block is constructed. But so we have 14 symbols. So what does this really means? This means that actually the frame configuration is not based on a slot, but is based on symbol. For example, let's look at the first frame type, which is 0. This one happens to be that all the symbols are downlink. But let's take a look at frame 44, which we have about 6 symbols in downlink. Then we have a flexible slots or flexible symbols. Actually, these flexible symbols are going to help the transition between downlink and uplink. And then we have a couple of uplink symbols on the same slot. So again, this is a little bit more challenging because of the timing that we have here in 5G midband, that the assignment is being done by symbols, not by subframes, if we take a reference the LTE signal. So as an example here, we see that here in time, we see the assignment. I use the same color coding for the downlink, the flexible, and the uplink. So with this understanding, what we have done is we have implemented an automatic way for our solution OneAdvisor 800 wireless, the ability to do it automatically, the way to find the frame and give us the opportunity to trigger just on those uplink symbols. So the process is fairly simple. So we find a 5G TV carrier, we find the SSB or the beam that is being transmitted out. From this beam, the SSB block, we're going to be able to get the downlink control information. That DCI is going to give us a frame format. So the frame format here on the right-hand side, we see the downlink and the uplink slots and symbols. And with that, basically, we're going to be able to get the same information that we got on the frame. We have 20 slots. This is the case of 5G midband. So we have 20 slots. We can zoom in one of them. Typically, we take the flexible slot to do the analysis. There are 2 reasons. One reason is that in the flexible slot, we have to get into specific symbols, but it's important because these flexible slots, we shouldn't expect to see any traffic from the downlink nor the uplink. And that's going to help us see if there are any external interference. We can actually trigger as well the uplink, but we're going to be seeing their uplink traffic. So it's useful just to kind of look into or to trigger into the flexible symbols because of that reason, because no traffic is being transmitted. And then when we trigger on it, then we're going to be able to see the spectrum. As you see in this specific example, the persistent spectrum we have selected in our slot 3. We have selected a couple of symbols, symbol 7 and 8. So basically, this spectrum happens to be in a 71 microsecond window. So it's very precise, but since the instrument is automatically synchronized with the 5G frame, always we're looking into the flexible symbols. So with that, let me just actually jump before I go into the post-analysis. What I'm going to do, I'm sorry, let me just go into my instrument. I happen to have a signal here. Typically, the process that I do is I start typically with a blind scanner. And the reason for that is sometimes we know, sometimes we do not know all the specifics of my signal. And by that, I mean center frequency, SSB, and all that good stuff. And again, that is important because we're going to be able to see with that information, we're going to be able to get the frame and then trigger on the uplink. So with the blind scanner, I did a quick blind scan here. I happen to have, as I mentioned before, not a very strong signal, but I was able to get my signal here. It happens to be 3.879 center frequency and 80 megahertz wide. And actually, this signal happens to be from AT&T. So anyway, this is my signal. This is why I'm getting reception. If I want to see my signal here in real-time spectrum, for example, it's going to be looking something like this, which again, my signal-to-noise ratio is not great. There is my signal, not very strong. And as you can see, there's some little things here that I don't know exactly which those are. But how we can do an analysis, because here on the real-time spectrum, again, we're just looking to frequency. We don't have any specific timing. So we're looking into everything, meaning everything that is being transmitted on this frequency, and that is both the downlink and the uplink. So we can configure our tags or TDD auto-gated spectrum. And again, because we got all the information already from a blind scanner, which is pretty straightforward, then we can do an analysis. And for that, typically we just open the tags test function. We go into an automatic configuration. I have everything in it. I can actually do search for the SSB. And yet again, it's important to do this search because with the SSB, this is the area that we're going to be able to get the frame format from. And then here we can do an analysis. In this analysis, let me just show it. So it's basically a similar example that I showed you before, just the signal-to-noise ratio is not as strong. But as you can see, we got all the frame information. We actually sometimes might be needed to have a little bit more distinction based on the location in which the measurement is being made. For example, here where I'm not getting a very strong reception, I can select my deviation. These deviations help me to find, because again, the 5G signal TDD is bursty. It's not that we have always a controlled signal being transmitted out. And the only thing that we have with some periodicity is the SSB, but the SSB happens to be at the beginning of the frame. But to make a better understanding about the downlink and uplink, this deviation technique is going to help us clearly see then where's my uplink, which happens to be here in my green areas. Great. So now I have full visibility of the frame. I know exactly where my uplinks are. and then I can trigger. And as you can see, this is the I can select any of these slots. I'm gonna select this slot because this is my transition. That is from downlink to uplink. So I want to select that one just because, again, as I mentioned before, on the flexible slots, there's nothing there. So well, shouldn't be anything there. It's just a transition period. So I want to analyze that specific slot. So remember, we have 14 symbols, and I'm analyzing that, and it happens to be in this flexible area. And actually, I can here make some more adjustments if I'm not happy with it. For example, if I want to avoid any propagation delay noise that I might be getting here, my slot 3, I can reduce it. I can, for example, just let's start from symbol 7 and go all the way up to symbol 9. So I'm going to reduce the width of what I'm triggering just to 3 symbols, symbol 7, 8, and 9. So I shouldn't see anything there. And yes, as an example, down here below, I have my frequency, and there's nothing there. I can just play apply. And this is how automatically I can see again on my 5G midband how the activity is on my flexible slots. And actually, as it happens to be, I happen to see 2 signals, and actually this signal right here, if I want to find it, I can just put a marker on it. I can do a pick search, and there it is. So I happen to see in this frequency a tone that it's somewhat intermittent. So anyway, it's interference? Most likely, it's very problematic. I don't think so. It's pretty narrow, and it's not a very strong, so shouldn't be too much of a problem. But the key thing here is that we're going to be able to analyze interference in 5G very easily and automatically with the TV automated spectrum capability. So anyway, I wanted to show you that quick demo. Let me just flick back into the presentation, and I'm going to be talking now about interference post-analysis. So when we get a report and we say, well, there's a PRV being reported out, that is a problem. And again, what's a PRV? That's a physical resource block. How with is that PRV? It all depends. So again, I have my same reference that I had before, frequency and power. I have all the subcarriers that I mentioned. And these array or these matrix of subcarriers and symbols, and more specifically 12 by 7 in LTE, 12 by 14 in 5G, that creates a PRV. So how with it's a PRV? And is it the same in 5G and LTE? Not necessarily. So as I mentioned before, 5G can have different numerology. So if in LTE we have 15 kilohertz subcarrier spacing, in the case of 5G, it can be the same 15 or it can be 30. What that really means is that if we get a report that says we have a problem on a certain PRV, that PRV, the width of that physical resource block can be either 180 kilohertz or it can be 360 kilohertz width. So again, just want to point that out because that's going to help us to characterize properly the external interference. So in the example that I have here on top, this is just a KPI that we receive from a management system. And as you can see, basically this interference signal, it's between PRV 19 and 28. Therefore, it's about 10 PRV, so it's about 1.8 megahertz if it is a subcarrier spacing of 15 kilohertz. Anyway, just wanted to make that distinction between the 5G low band and the 5G mid band, that they have different widths. Now, let's talk about the external sources of interference and typically how they behave. We can group them in three different groups or three different classifications of interference. The first one, let me call it the wideband interference. Typically, we've seen that from broadband amplifiers. So that's anything, in reality, anything beyond 2 megahertz that can be viewed as wideband. And the best way to look or analyze or hunt for this interference is with a tracking mode that is called channel power, because we're going to be able to check the power of the entire channel. And again, this is the way that we are going to be able to find that interference much faster. First, understanding how the interference behaves, which frequency it is, how wide it is. And with that information, we can configure different tracking modes in the system to find it, to find the interference much faster. Now, the other group that we can view, it's narrowband interferers that they're present but are very narrow. Anything that is below 2 megahertz can be considered as narrowband, and for that we are going to be able to put a tracking mode in the system that is based just on RSSI, or received signal strength indicator. And the third group of interference, we can view it as frequency hopping interference. Typically, this is very common in welding machines that I mentioned before, that they basically go in one frequency and they change frequency in a very defined pattern. So here we're going to be able to find the bandwidth in which that frequency is hopping along. And with these, we can select the tracking mode that is called peak power. So peak power, we define the bandwidth in which the peak power is being tested. And in this area, that's the only area in which we're going to be making measurements. So again, we're not going to be looking into peak into the entire channel, but just in the area that the interferer happens to be. So these are the three main classifications, and for each one of them, we have defined a specific tracking mode capability: channel power, RSSI, and peak power. Right, so sometimes even those interferences are not always present, meaning that we do the analysis, we look into the spectrum, and everything is clean. The interference probably happens in all times, or even the interference itself, it's very intermittent, so it's not always present. So how can we analyze those interference signals? We can do it by logging or recording the spectrum and then do a post-analysis. So we can certainly save the spectrum, and we can do this analysis of the spectrum with OneViewer. OneViewer is the applications with which we can analyze the signal. It's a freeware provided by the AVI, and all the recordings been made by OneAdvisor. So let me give you an example, actually, before I go into the interference finding topic. So let me just go into, this is my OneViewer application. As you can see, actually, this is a 5G mid-band signal that I recorded. And I'm just replaying it. I can just pause a replay, and that's fine. But I can change the view of my signal just to have a kind of a better representation. I can view it as a spectrogram, or I can also view it as a real-time spectrum, or even I can view it as what we call the RSSI. This way, if we have different interference signals and we want to know the how fast they're changing, we can basically select markers and say, for example, okay, let's look into the first marker. I want to put it right there, that I know it's kind of, it's a little bit of a power change. And as you can see, that it's going to give me a trace on the right-hand side that is going to give me the timing, the histogram of the power that I see on that specific marker. If I have multiple of them, just here as an exercise, I want to put another marker. So I can put as many markers as I can see intermittent interferences. And here on the right-hand side, I'm going to be able to say the behavior of them in time. Okay, so that's pretty helpful to find the interference occurrence. But if I go back into my signal itself, I'm going to go back into my spectrum. There are other ways in which we can analyze a signal. And again, this has already been recorded. I'm just doing a post-analysis, and I can have or enable different traces, for example. So here I enabled the average, mean, and max hold. So I can see how, in that period of time, how that signal changed. Or I can go and do something that it's probably more helpful, which is I can put limits. So here I'm going to put a limit. I created a mask here and say, okay, for any time that the signal exceeded the mask, actually here down below, I can see the events. So let me just pause for a second, and there are blue indicators here that it's telling me in which point in time the signal actually exceeded that spectrum mask. And again, this is important because this is we're tracking for intermittent interferences, and it's something that shouldn't be there and happens once in a while. Instead of replaying the whole spectrum multiple times, here with this spectrum mask and post-analysis capability, I can just jump into each one of them. For example, here are all my events. I have 33 events, and I can just jump into each one of them. And again, this is just as an example, but if we're analyzing the uplink and we're analyzing kind of that area that I have an intermittent interference, with this capability, I can easily find where that interference actually happens. And if so, I can then analyze, again, the profile of that interferer. Okay, so this is how we can do a post-analysis or post-process analysis of interference signals, again, with the purpose of having a complete profile of that interferer. Okay, so now let me go back. And now that I know how the interference looks like, because I was able to do it automatically in 5G TED with TED at a given spectrum, and trigger at the right time, and then I know how the interference looks like. Even if it's an intermittent interference, I can do a post-analysis of interference. Now that I know how the interference looks like, I want to find it. I want to do interference hunting. So for these, we can do it in as I mentioned, a couple of ways. We can do it automatically with a solution that we have that is called Interference Advisor. Interference Advisor basically takes all the measurements from the one advisor, and it puts all those measurements in a map, in a heat map. So it takes multiple samples and then makes a measurement. The other mode that we have with Interference Advisor is spectrum clearance. This is very useful in areas where we don't have anything being deployed yet. For example, if there's an area that there's a new 5G mid-band to be deployed, one recommended principle is, okay, before you deploy it, make sure that the spectrum is clean. As it happens, in this specific example, I was actually looking for that spectrum before the 5G were deployed, in mid-band, and I did a drive with the spectrum clearance. And sure enough, I found a problem in one area. So here, for example, everything was clean, and in these areas that actually the system automatically, it's putting the measurements with red outline on the circles. That indicates that it exceeded a limit that I predefined, and the limit was -100. But in any case, I can select each one of those events that exceeded, and I can see the power level. In this case, the power level was -72. I can even get the spectrum of it, and as you can see on the right-hand side, there's interference for sure. And as it happens to be in this specific location, which actually it was later on found and mitigated. But this is one way of doing the 5G analysis when it's not yet deployed, to make sure that the spectrum is clean. Now, if it has been deployed, then is the traditional interference hunting technique. And again, here with Interference Advisor, as I mentioned, with the understanding how the interference behaves. This happens to be, for example, an RSSI. So this was our tracking mode. Automatically takes all the information into a map, and then based on the number of samples, so this is just doing a drive test, we keep driving, and automatically is going to let us know the suspect area of where the interference is coming from, and then it's going to give us even driving directions based on all the sample data. It's going to be able to zoom in and say, well, it's in this location. Now, one important aspect here when we do this type of interference hunting is use filters. It's important to use filters because these filters is going to be able to eliminate any power from the downlink. So that way we're going to be able to only to concentrate and to increase the sensitivity of my receiver, my spectrum analyzer here by using filters.
Eduardo, there is
Yes.
a question based on that screen that you just showed. The question is, what are the RF filter characteristics in your diagram?
Yeah, these filters, they're different based on different band, different uplink frequency that we're looking for. And typically they might have kind of a rejection of 30 dBs, meaning that everything that is outside of that band is going to reject or is going to attenuate by 30 dBs. So, but yeah, we have different filters based on the uplink frequency band of interest. But certainly we need to pick the right filter that it's going to be the one that we're going to be using for the uplink that we're testing on. Okay, so now that we have found the location, so the next step is to find the device or the source of that interference. So typically this is being done by a walk test. And doing a walk test, having my instrument, my OneViewer 800, using a directional antenna. And this directional antenna is going to be able to find, doing a walk test. And actually here in the real-time spectrum, I can even put a sound indicator. And this is going to give me the sound of the strongest interference signal that I'm looking for. So again, remember these, it's already been configured, and I'm only looking into the uplink. I know how the interference behaves. And in this example, this is my interference. And I can put a sound indicator. So that's actually is going to help me to find that interference by audio signals, as well as visibly, I can see from which direction the interference signal is stronger. And then by just walking, I'm going to be able to find where that interference is coming from. So this is what I wanted to cover. You can find more references here. I put a couple of notes references. One, it's on the instrument that I used. Is a OneAdvisor 800. You have a lot of information here on our website. There are some videos on how to do testing on the tracking modes that I explained. We have posted a couple of videos on finding interference using those tracking modes. Same with finding interference in TEV. So you can find more how to test videos in this website, as well as we put it another page on our site for the interference advisor. So this is the automatic way of dry testing and finding interference. So with that, I'm going to be opening for any additional questions you might have.
So there is one, I'm not sure who asked it. It doesn't have a name on it, but the question is, do you have examples of what interference may look like in spectrum for different interference types? Example, welding machine, broadband amplifier, etc.
We do, yes. So I think you're looking for the spectrum signature of those, and we can send those over via email for sure. Of welding machines, amplifiers, video cameras. Yeah, for sure. We can certainly send those over.
Okay, and then the one other question was, how can we access the recordings? They'll be on our website. It takes a few days to process how we put them up there, but they are on our website. Under webinars, you go to resources, you can look for webinars, and these are all categorized as the best practices series for uplink interference. You should be able to find them. The one from last week should be there soon. I will check to see if it's been added today. And then this one today will get processed and should be uploaded by next week. So thank you for your interest. We will send out a post-event email with a copy of the slides that Eduardo used. He always PDFs these, and we make those available to you as well. And then there is another question. Does Viavi offer on-site training on this equipment to find interference?
We do, yes. Yeah, that's why actually at the beginning I posted those emails from Dan Ismaisha and Steve Gale. You probably know them. These are our key subject matter experts and provide training for interference finding.
Great. So, and also if you don't have those emails or you don't remember them, Dan's is always kind of tricky because he has a unique spelled last name. You can always go to our website and fill out the form to have sales contact you, and we can get your trainings questions addressed in a way that works best for you. So I think that's it. Let me double check for any other questions, I think. Oh, there is one more. What have you found causing 3.5 TDD external interference in the field? Any known devices?
Yeah, the only one that I have found happens to be one of those cordless phones that I mentioned before. That's the only one that I have found for mid-band. Most of the other ones, certainly cable, TV interferers that are leaking, or video cameras, even the welding machine example, all of them happen. I've seen them in the low band. Mid band only have been the case of cordless phones.
Great. Well, that's all the questions we have today, and we're coming up on the hour, so we'll be able to close out just a bit early. I want to thank you, Eduardo, for another great presentation. You offer so much technical expertise that I know is appreciated by our attendees. Thank all of our guests for joining us today. Everyone, as I mentioned earlier, everyone who attended will receive an email with a link to the document, and we'll have the recording on the website in a few days. We hope you found this session valuable, and as you log out, you will be presented with a survey We do appreciate your feedback on that survey. We are using it to plan our next sessions. So I take a few minutes to answer. I think they're just 4 short questions, real quick, and appreciate you answering those for us, and wish you all a great day. Thank you.